Hello and welcome to Dr. Nakul Gangolli
Thank you, John.
of UCR, University of California, Riverside fame, who is going to be our interview subject for the subject of a research astronomer.
Oh, thank you for having me, John. Nice to see you again.
Yeah, we used to live together for like 5 years.
Yes, we did. As
Yeah.
roommates.
Okay.
All right, let's get started.
Okay. Yeah. So the first thing I would like to ask is just a general question about what your type of research you do and like your academic background, if you wouldn't mind.
Yeah, my field of astronomy is typically known as extragalactic astronomy and cosmology. So essentially everything that's outside our galaxy. And I'm not exactly sure what you brought up in class specifically, but what I did was I studied roughly the first 1 billion years, 1 to 2 billion years of the universe's history.
Yeah. So to be clear, this is for my conceptual physics, not even algebra-based class, not for my astronomy-based class, which I'm concurrently teaching.
Oh, I see. Okay,
Yeah.
they're fast. Okay. In essence, I study the evolution and the formation of galaxies and what we consider the large-scale structure of the universe during very early times. Because in essence, during this time period, the universe looks completely different than it does today. And what I did was that I made simulations of these galaxies happening or this evolution occurring by using what we call N-body simulations, where we assume that everything interacts only through gravity. And I ran a lot of these types of different simulations and simulated galaxy properties from these simulations to then create predictive models of what we would expect these galaxies to look at, what kind of observed properties they have, and how they then generally interacted with their local environments. And this was in the grand scheme of solving questions about this time period known as the epoch of reionization. So this was immediately after the Big Bang. The universe was very, very hot, but eventually, as it expands, it also cools down very rapidly, up until a point that it got so cold that the only gas that was left was what we consider neutral gas. Then, when the first stars and the first galaxies turned on, eventually this reheated the gas such that we can observe the galaxies and the stellar light that we observe today.
Okay.
And so, yeah,
Yeah. Nice. Uh, yeah, I just happened to actually be reading about this a couple hours ago for
awesome.
my other class.
I'd love to. I mean, if you ever have any questions in more detail, I'd be
Yeah,
happy to answer.
nice. Well, for now, what drew you to physics against other areas of study, and why specifically astronomy?
So, oh, what was the question?
What drew you to physics against other areas of study?
Yeah, well, I grew up in a family of scientists. My dad was a chemist. My mom was a biologist. I thought I should fill the physics background of this, and specifically astronomy and astrophysics. And the reason I loved astronomy over other fields of physics in particular is because I really loved the pretty pictures. I was born roughly when the Hubble Space Telescope went up and we started receiving all these images. And I think when I saw how cool those Hubble Space Telescope images look like, and then I saw the images from other telescopes, and then when you watch TV all the time, I was a big TV watcher and I'd love to watch the Cosmos with Carl Sagan and a lot of other different astronomy shows. So that's why I really got interested in astronomy in particular, because at the end of the day, people, and me in particular, I just the beautiful of space is derived from almost its very violent nature. So there's this really cool, intricately linked dynamic that happens, which is why I was mostly interested in, astronomy specifically.
And yet you don't study cannibalistic galaxies.
Actually, no, that is a field of physics. So that's a field of astronomy that actually some people at UCR study.
Oh, okay.
I mean, in the sense that when they eat up galaxies, it's like you have very violent galaxy mergers. And again, like space is mostly empty, but places where it's not empty, it's explosive. It's we have a funny saying where the biggest particle collider is the universe.
Mm, yeah. Okay, and let's see. You I need to take that question out because I've already done it and I've gotten tripped up twice now. But do you prefer fundamental research theory or more applied work?
I was substantially better at the when you say fundamental research, again, that's a very interesting.
So, research that isn't for that is to learn about physics and astronomy and isn't for, say, applications in engineering
Uh,
like you would see in condensed matter
I
sometimes.
mean that is what astronomy
Yeah.
usually is. It's like there's not so much else going on out externally, but as someone who worked a lot with simulations, I would say I was more on the theory side of
Okay.
astronomy, like astrotheory. Because again, what I did was I would simulate what the universe, a bunch of universes. So I'd like to say that in my entire PhD career, I made about 4 universes.
Oh, nice.
Yeah. I, yeah.
So, yeah, and with all these simulations and all these uh this programming, do you think that the programming and the mathematics and the that side of physics has gotten easier, or is it still something that you struggle with?
It's something that with practice, it does become a lot easier to do.
Okay.
Again, like everything, physics is when you see a problem 100 times, it becomes very you kind of just do it by muscle memory.
Yeah.
So like with all these simulations, I've run so many of them, and I understand the inner workings of them only because I've played around with them for a very long time.
Okay. Yeah. And this is a question from a student. After you've worked in the field for as long as you have, would you say your curiosity in some specific areas of your work has increased or decreased? Are there things that bother you that it's not exactly explained?
Um, I would say yes, that both increase and decrease depends
Ugh.
on it does depend on the question that we answer because once we answer one question, right, the curiosity for that question is sated,
Yeah.
but there's always something else. So, for example, in one of my other research projects, it was we were able to figure out uh, this physical effect has this effect, right? But then how does then that steamroll into what we see today? And so, unfortunately, we're never going to have like infinitesimal resolution. So
Mm.
there are always going to be more questions as to the why, the how, the when, um, and those I don't think bother me at all because it allows future generations to have problems to solve. If we solved it all today, then what's the point?
Hmm. Okay.
Yeah,
Yeah.
so I'm not upset.
But what are the biggest unsolved problems in your field right now? Speaking of problems that need to be solved by future generations.
Oh, of course. So right now, in terms of for astronomy as a whole, the biggest questions are, what is dark matter? What is dark energy? Those are still very unknown quantities.
Yeah. Could you explain what dark matter and dark energy are?
Yeah. So
I think that's a question actually deeper down, but yeah.
okay.
No.
But so in the 1970s, by looking at the dynamics of galaxies, we realized that portions of the galaxy were spinning a lot more quickly and a lot more rapidly than we had expected them to be.
Okay.
And so, for example, if you imagine that, you would expect that stars at the very edges of the galaxy should be moving more slowly than the stars at the center of the galaxy. Like that would be a very
Yeah.
intuitive thought to have. And this is what people originally had thought was happening. But when we actually looked at the velocities of the stars at like the edges of galaxies, we found that they were moving just as fast as the stars in the center of the galaxy.
Mm.
And the only way you could really explain this, unless you're going to pull up some weird Newtonian stuff that I don't subscribe to, but other people might, was that there was an additional source of matter.
Yeah.
And uh, ever since there have been other future observational detections or observational evidence to indicate that there's this thing called dark matter, which the reason why we call it dark matter is because it doesn't interact at all through light. Telescopes can only see light. So if we can't see it through light, it's dark,
Yeah.
effectively, right?
Yep.
Um, dark energy. So let me put it this way: dark matter is a unseen force that is keeping galaxies held together. Dark energy, on the other hand, is a we don't know what dark energy is. We know it doesn't interact through light, but what we do know is it's causing the expansion of the universe. And maybe you've gone over this in your class, but the universe is expanding at an accelerating rate, which means that it's growing faster and faster, second by second.
Yeah.
But we don't know what is causing that. And again, we know it doesn't interact through light, hence we call it, dark energy. We also don't know what it is, so dark. Astro people are very creative group of or a group of people. But
Yeah, I
yeah.
mean, yeah, there's all the constellations in the sky.
Yeah.
There, that totally looks like a pair of scales of Libra.
Yeah, sure. Yeah. Or that definitely looks like a person,
Yeah.
Orion or Sagittarius.
Yeah.
But,
Orion does look kind of like a stick figure, honestly.
okay, that one was a bad example.
Okay, so what discovery or breakthrough has had the most unexpected impact, and what impacts do you foresee occurring soon?
So, that is a very, very interesting question. Uh,
Hmm.
uh, when you say in my field in particular, my field of phys or my field,
Astronomy.
astronomy in general, I would say astronomy in general, again, dark matter, dark energy, the biggest questions and the most probably important discoveries in astronomy in the last 50 years, at the
Okay.
very least.
Yeah, so the next question is actually what is the biggest unsolved mystery, and you just kind of went over that dark matter, dark energy.
Yeah.
Okay. So what tools or technology do you rely on most in your day-to-day work? So you do simulations. Uh, in order, I know you don't do it, but can you also give me a little bit of background on what like an experimentalist might use in their
Yeah, of course.
day-to-day?
So, from a simulation side, what we use are high performance computing clusters, or in essence, we use what we call, simply put, supercomputers.
Yeah.
Computers with thousands, if not tens of thousands of cores to run these really, really big simulations. And usually to interact with these we interact with the computers in the same way, I think a lot of computer programmers interact with computers, whether it's through, Bash to run Python scripts, C++ scripts, Fortran, and these are like coding languages that we definitely use. But for most of our analysis, and if anyone is wants to get interested into doing astronomy, I cannot recommend more learning Python. Right, like get your hands dirty with any sort of kind of Python. Um,
Python is programming language, not just a
That's
type of snake
that's
that
kind
you
of thing. Yeah,
can.
Python is a computer language. If you want to actually work on building a simulation, the simulations themselves, then you would want to learn more about C, C++. But again, like if any of the people listening to this are going to be interested in doing physics, coding, learn some kind of coding, take a coding class. Hell, try to do a double major in computer science.
Okay. I
Uh,
didn't do that, but
well, again, when we were because when we were coming up, it was a much different world, I
yeah.
think. But now a lot of it is computing. Actually, you know what? Learn AI, learn machine learning. You're going to be using a lot of that because I'm pretty sure you're going to ask me where the field is moving in the future.
Yeah.
That's also kind of where it's moving. That's where it's moving.
Okay.
For better or for worse, like machine learning, learn artificial intelligence, generative AI, start getting into those things. But anyway, tools. We use a lot of machine learning. We use a lot of AI. When you're talking about observations, we have a couple of different types of telescopes, all at different wavelengths that we call it. So we have ground-based telescopes, which are, as you say, on the ground, and space-based telescopes that are in space. However, you could further diverge these groups into, for example, visual detection telescopes, which use visual light. So when we talk about observation, sometimes you'll see people talk about visual telescopes, which observe space in the visual spectrum. So from red to purple kind of thing.
Yeah.
But then we also have UV telescopes. I believe there are some telescope. I think I don't remember off the top of my head now which one Keck is,
Okay.
but I don't know which wavelengths they are. But I think those are in the UV range.
Yeah, I knew
Again,
this a month ago.
yeah, yeah. But like you have UV telescopes, you also have infrared telescopes. The new James Webb Space Telescope, the one that's up in space right now, is what we call an infrared telescope because it makes observations in the infrared. Um, you also have X-ray telescopes like the Chandra Space Telescope. I think uh, and then you also have radio telescopes. Radio telescopes that make observations in the radio waves
Okay.
with radio waves. So you run the gamut, and then of course microwave. You might have heard about your cosmic microwave background.
Yeah.
Very, very, very big field in astronomy. Very important. Actually, I would say that's another important, one of the most important discoveries, the cosmic microwave background.
Okay.
But anyway, yeah.
Okay. And then uh that is it for the general questions, and now we're going to go on the questions that were specifically asked for you
Okay.
for astronomy. And the first one is, how do you study cosmic phenomena like supernovae or black holes? Sound doesn't travel through space, but do you use electromagnetic waves or something else?
Yes, so we use electromagnetic waves. That is how we detect all light. So essentially, for the past, I want to say thousands of years till now, we've essentially been using electromagnetism and light to do astronomy. However, we are starting to enter what we consider the multi-messenger era of astronomy. And now we're not only able to detect electromagnetic waves, but we're also able to detect neutrinos, and with LIGO, gravitational waves.
Okay.
And so now we could use all of these in tandem to build a much more rounded picture of what we would observe the universe to be. So, for example, when you're talking about supernova, right? Supernova we could observe with light, but we could also observe them with neutrinos. And we're actually able to observe a supernova in real time because we were able to detect a burst of neutrinos coming from some part of the sky. And we were able to then turn all our telescopes to that part of the sky to see supernova. LIGO has been able to observe uh, black hole mergers through the observations of gravitational waves.
Yeah.
And so now we don't need just electromagnetism. Electromagnetism and light is still in my opinion, objectively still the most important um, observational tool that we have. But hopefully in the future we can start giving more weight and building better detectors for these gravitational waves and neutrinos.
Okay. Um, And when talking about constellations, I know the Greeks are the ones who are considered to be the inventor as far as I know, but my question is more of what made them think of interpreting animals and creatures. I think we went over this uh, when we were just spitballing.
Yeah, so one thing that as someone from a different cultural background, not necessarily from the Greeks, because it wasn't only the Greeks who were able to build these constellations.
Yeah,
As someone of Indian culture, I was brought up with a more Indo-centric view of cosmology and the constellations that they use. But you had the Egyptians had their own, the Mesopotamians had their own
yeah,
versions, Chinese, Mayans, Inca, and almost every culture you go to at some level, they have their own set of constellations because in the ancient world, that's how you measured the time of year it was. It
yeah,
wasn't only just like the sun and the moon, but it was also using the constellations when they would appear, and it's how they would track time.
yeah,
And so it was a critical aspect of a lot of other different cultures. I just think uh, since the U.S. in particular, is derived from what we consider Western
yeah,
cultures, the birth of, I guess, Western astronomy can be largely attributed to the Greeks.
yeah,
Hence why we learned about the Greeks.
yeah. And this is something that I wanted to uh as much as I could, I wanted to combat that when I was starting out this lecture series. It's just that a lot of the history about the history of science and the history of physics from a non-Eurocentric viewpoint has been lost or obscured. But
Yeah.
I have found a couple books I'm trying to read right now that
Yeah.
are getting more into that that'll like introduce into
I mean,
future classes, I
yeah,
believe.
I feel like the history of astronomy could be its very own different class, but
Yeah,
it is amazing how vastly disparate cultures
yeah,
that had never interacted, actually roughly derive very similar, similar calculations to, measuring time, measuring the radius of the Earth, et cetera, et cetera.
okay, yeah. I think that's a good idea for just like general physics and like general science is that it is reproducible. So I am actually going to skip ahead in our list just because this kind of reminded me of this, and
Okay.
I'm going to ask you the alien question, which is uh, do you think that there are aliens, and how would you communicate with them? Especially considering that we have actually tried to communicate with them using these things that are, like you said, constant cross cultures, constant cross
Yeah, so
space, I guess.
I want to say it is the Voyager space mission.
Yeah,
Yeah, exactly. Which has like the plaque, which shows how we look, some basic math equations to show that we can do math.
yeah,
Um, I guess so. Do I believe aliens exist? In the sense that do I believe that life exists outside of Earth? Yeah, on other planets. Yes. In the entire universe, absolutely. It is so, so, so massive
yeah,
that I just think it's impossible for it to not exist elsewhere. Now the question then becomes, and how do we communicate with them? How
yeah,
do we talk with them? That is a substantially much more difficult question because even the closest star system to us is 4 light years,
yeah,
which means that if we send a message out with light, it will take it 4 years to get to them, 4 years to get back to us. So a total, we say hi, we'd have to wait eight
yeah.
years to hear hi back.
Yeah, when I was talking to Mr. Baker a couple days ago, he brought up that there is strong evidence that there isn't life within 55 light years of us because we've been sending out radio waves for about 110 years.
Yeah. That would make sense.
Yeah,
And the other thing that we have to be careful about though is like the further light travels, the weaker that signal gets.
yeah,
And then you have to kind of pull that out from all of the signals that are coming from space itself,
yeah,
which becomes exceeding. So maybe there is a life within 55 light years, but it's just very, very, very difficult to pull some tiny signal out,
yeah.
from the cosmic background.
Yeah. Yeah. Oh, and could you just briefly explain what the cosmic microwave background is because you've
Yeah.
brought that up a couple times now?
So okay, when I talk about so there's two different so the background that I'm talking about is everything, like light from everywhere across all wavelengths from everything.
Yeah.
The cosmic microwave background specifically is the signal that is essentially left that was left about a couple 100,000 years after the Big Bang. So as I mentioned before, after the Big Bang, the universe was a hot quantum soup of particles. The basic particles, even like not even protons and neutrons, like particles that make up those. It was just a hot cosmic soup. And eventually, as the universe expanded, it also cooled down. And during this process, the particles finally kind of stuck together. So in the first like 1 billionth, even 1 millionth of a second in the universe's birth, there was no such thing as protons and neutrons,
Yeah.
right? That only happened a little bit later. But because of this, light interacted with matter. So you could not distinguish between whether something was light or something was matter because they were all kept interacting with each other
Yeah.
and kept getting absorbed, emitted, whatever. The cosmic microwave background is that last moment that light and matter were part of the same soup.
Okay.
After this period, the light free streamed throughout the universe. It never interacted with anything again until it finally came to us,
Hmm.
as what we observe. And that is what we call the cosmic microwave background.
Okay.
Because it is because we observe it in the microwaves.
Yeah. Where I think I've gone over the different types of electromagnetic radiation
Yeah.
at various points. So, yeah, microwave is just a specific. wavelength
Yeah.
of
Oh, yeah.
electromagnetic radiation.
Yeah.
The Mars was for dark matter was dark energy. We've gone over that. And then uh what happened to the stars that we used to see in the Inland Empire? Did they disappear or is there light
Light
pollution?
pollution.
Yeah,
Light
okay.
pollution. Light pollution, also dust makes things very, very difficult. So the more dust there is in the air, the more light's absorbed, the more difficult it is to see.
Okay. Yeah. And then since the sun is technically considered a star, and when a star dies, it can become a black hole, would the sun ever possibly become one?
No, it will never become a black hole because it is not massive enough to do so.
Yeah.
In order for in order for a black hole to form from a star, it first must undergo the supernova process. But in order to undergo the supernova process in the first place, a star should have enough mass to have supernova to
Yeah.
go.
And I
The
think it's about 25 times the mass of the sun.
it's For a star to go supernova, it has to be at least 8.
Oh, okay.
To turn into a black hole, it's about 20 to 25.
Okay.
Yeah.
Okay. And then you talked about the future of astronomy. So that we kind of went out of order just because like
Yeah.
we were free flowing. But one more thing that wasn't on this list but has been brought up in the last couple uh, interviews I've done is a Veritasium video,
Oh.
which says that of energy is not conserved in an accelerating universe because time symmetry is broken by the acceleration of the universe. Do you have any idea
I
about
would
this?
I would have to watch the video, but the problem the underlying argument that as to why energy is not conserved when in an expanding universe is because you have a force that's causing this expansion rate
Okay.
to occur, right? And when you add energy, that energy has to be coming from somewhere from the conservation laws.
Okay.
But the problem is that we don't know where this vacuum energy is coming from. We don't know what its source is. So we can't say that it's being conserved or not because it's the expansion of the space itself.
Okay. Okay. Yeah.
In terms of the time symmetry stuff,
Yeah.
that's actually
Symmetry. I know you really like Noether's theorem. That's just something that is very, very interesting, but is a little bit outside of
yeah,
the
yeah,
level of like a conceptual physics class.
yeah.
But I think that comes to the end of all the questions that were asked by students or asked by me. So before we end the interview, I would like to ask the like standard end of interview question or end of job interview question. Are there any questions that we should have asked?
Um, I don't think so. I think you've at least asked the big questions.
Okay.
I can't think of anything off the top of my head right now. Um, but yeah, I think I don't think you all asked very good questions.
Awesome. Well, thank you again for
Of
coming.
course,
You've been a very good interview guest, and I'm glad for you that you took the time out to
of
speak to
course.
me and
Thank you.
speak to the students.
Thank you for having me. I
Oh,
appreciate it.
yeah. Bye.
Bye.